So we've reached the point where we introduce the most important object of this entire course, and that is a stochastic process called the Brownian motion, a family of random variables indexed by a parameter t, which is not just a natural number, like for the discrete time stochastic process we've seen so far, but a real number. And to start with, we'll take it just in a closed interval, 0, 1. Now, what is the Brownian motion? Well, it is many things. It is the simplest non-trivial stochastic process indexed by a continuous parameter that one can think of in many ways. It's a quintessential object that's used in a whole range of models. In finance, of course, that's going to be some of our applications. It's used to model changes of the relative changes in the price of a stock. It's used in biology. Brown was a biologist and he was studying the motion of pollen. Einstein used it to prove the existence of atoms. It has a very rich history and it's really ubiquitous to all of the sciences. From a mathematical point of view, you could see why that is, and we'll see why that is. Why that is, to me, it's because it's really the building block of stochastic calculus. It's the stochastic process from which you build all of the other stochastic processes. It plays the role in stochastic of the indicator function of an interval in deterministic calculus, right? So we'll see that it's closely related. It's a stochastic analog of a natural Gaussian stochastic analog of the functions that sends a real variable to 1 if this variable is below t, and 0 is if this variable is not in the interval 0t. So you remember from any analysis course that when you build, say, the space L2 or all sort of spaces of functions, you very often do that by taking appropriate limits of simple functions, so linear combinations of indicator functions such as this one. And we'll see exactly in the same way that a lot of stochastic processes can be built by taking appropriate linear combinations of the Brownian. So we're really building the brick of all of stochastic calculus. Okay, what does it look like and what are these basic properties that we would want from such a fundamental process? Well, let's see, there's 4 of them, and the key thing we're going to have to do is to prove that the Brownian motion exists, right? When we state the properties that we want from such a basic building block, maybe we're unlucky and maybe we have stated a range of properties that contradict each other and you cannot find a process that satisfies all of them at the same time. Very fortunately, the Brownian motion does exist and we will construct it. Now, let me actually do a little spoiler alert here and tell you how we're going to construct it, because it also helps you understand what it is. Now, this function here, this indicator function of 0t, I could expand it, right, in the Haar basis. We've just seen when we worked on dyadic martingale that the Haar functions form the basis of L2 of 0, 1. So this is one way of writing the indicator function of 0t, just expanding it into the Haar basis. Now what we will see is that a very neat way of constructing the Brownian, and that's the approach we'll use in this course, is to take exactly the coefficient of the indicator function of 0t in the Haar basis, but not do that as a weighting for linear combinations of the Haar functions themselves, but use instead IID Gaussian variables. So somehow what the Brownian motion is the analog of the indicator function of 0t when you randomize the basis, and instead of taking this basis of L2, you take IIG Gaussian variables, and so you build a Gaussian analog of the indicator function, right? From a purely analytical point of view, that's what the Brownian is. Now, from maybe a more probabilistic point of view, it is a very natural stochastic process. Now, natural in which way? Let's have a look at the properties. The first property is, well, we're going to initialize the Brownian to be constantly 0 at time 0, right? That's just for uniqueness sake and having a well-defined process. You could initialize somewhere else. It wouldn't matter. It would just shift your Brownian motion. Now, what really matters are the probability 2, 3, and 4. Probability 2 tells me that I'm asking for all of the increments of the Brownian to be independent, right? So I'm thinking about what are the variation of that process, and I want to keep things as simple as possible, so I'm not going to have any correlation between these different increments. So if I'm looking at the Brownian on different times interval, t1 to t2, t2 to t3, t3 to t4, and so on and so forth, I want every possible increment to be independent of the other increment, as long as you don't create non-trivial intersection between those intervals. Now, an increment of the Brownian, and the way the Brownian changes, well, I want this to be random, and the simplest or the most quintessential random variable I can think of is the Gaussian. The central limit theorem tells me that this is a very generic kind of variable. So, right, so I'm going to do that. I'm going to take the increment of the Brownian to be centered and Gaussian variables with variance t minus s. Okay, again, if you think from a probabilistic theory building point of view, independence is the simple form of relation between a family of random variable, and then Gaussians are the simplest kind of random variable I can think of in some ways. So I'm building a process which varies exactly in this canonical sort of way. Okay, now from a more modeling point of view, of course, people like Einstein or Bachelier in finance, they were observing this behavior in practice, right? In the physical reality they were looking at. So they were expecting independence, and they were looking at things that were behaving in this sort of Gaussian way. So that's why they wanted to know if you could model that with a mathematical object. Now, one of the key property also is that we're going to ask for almost sure continuity of the path of the Brownian. It takes a bit of time to understand what that means. Now, remember that for every t, bt is itself a random variable. So what I'm writing here really is the probability of the set of all those omega for which the function t goes to bt of omega, which now is a genuine function because that's a real number. That's what we call a path of the Brownian. You pick a value of the probability variable, and then that gives you a certain curve if you imagine the graph of that object, and you're asking for that curve to be continuous. Now there's infinity many such curves. There's just as many of them as you have point in your probability space omega, and we're not asking for every single one of them, we're not asking for every omega for these trajectories to be continuous. There might be some discontinuous trajectories, but we want the set of all the omegas that give rise to a discontinuous trajectory to have probability 0. So you know that as soon as you've thrown away a certain set of measures 0, then on the complement of that, all of your trajectories are continuous, right? And remember, by trajectories, I mean such a curve. So one way to picture that is that, your Brownian has to start at 0, but you give me an omega, and I get a certain trajectory of the Brownian, but you give me a different omega, and then I'm going to get a different trajectory of the Brownian, right? So this thing in purple and the thing in red, they are two different trajectories of the Brownian for two different choices of omega. And it may be that for some omega, you get something weird with some jump. Okay, that would be a discontinuous trajectory. This can only happen with probability 0. So of course I can draw one. In fact, I could draw countably many if my set omega is uncountable, but only on a set of probability 0. Okay, so I've given you already a hint as to the way we're going to construct the Brownian. There are many different constructions that all have their advantages in teaching you something about the nature of the Brownian motion. There are some very functional analytic constructions that have the advantage of being fairly direct consequences of powerful theorems in functional analysis. Now, obviously, we're not going to use those in this course because I'm not assuming that you've taken a functional analysis course. There are constructions that really make a lot of sense probabilistically, where you construct the Brownian motion as a scaling limit of a random walk. One other way that I haven't talked about yet of thinking of the Brownian motion is that this is really a continuous time analog of the random walk on Z that we've been talking about a lot in the discrete time stochastic process part of the course. So, you want a continuous time analog. What you do is you start with your random walk on Z, and instead of using Z, you start using half Z and random walking on with side step 1/2, and then you start random walking with side steps 1/3 or 1/4, and then you refine your partition, and you want to show that in some appropriate sense this family of discrete time stochastic processes have the limit. And you could do that, and that would be a way to construct the Brownian motion. But the way we're going to do is we're going to do it using the dialectic martingale, using the Haar basis, and that has two advantages. It really highlights the role of the Brownian motion from the point of view of an integration theory, or from the point of view of calculus, as being the analog of characteristic functions, indicator functions. And it would also make it easy for us to understand the regularity property of the Brownian. Well, we know it has to be almost surely continuous. That's part of the definition. We'll see that it's better than that. It's uniformly continuous in a nice way. It's called Hölder continuous of parameter alpha, strictly smaller than 1/2. But it's not that good either. In particular, it's going to be nowhere differentiable. And that's an important fact that we're going to have to understand, because this fact is exactly why we cannot develop a differential calculus adapted to the Brownian, so a stochastic version of differential calculus, in a way that really mimics what you've seen so far in your career as an analyst, as an undergraduate analyst, right? The typical approaches to differential calculus will fail because the Brownian is nowhere differentiable. On the other hand, the approaches to integration theory, building integration theory on the simple function, that's going to work, and that is the approach we'll take to calculus. So as I just mentioned, we're going to construct the Brownian as a linear combination of IID Gaussians, putting as coefficients exactly the same coefficient as you would have if you were to decompose the indicator function of 0t in the Haar basis. Now, so what are we going to have to show, right? In order to show that this indeed defines a Brownian, we're going to have to show nice convergence property of that series in an appropriate space of stochastic processes. So to do that, we need to understand the behavior of IID, of infinitely many IID Gaussians. And that is really the point of lemma 3.3, which is the first thing we need to show. So this lemma tells us the following. If you have a sequence of Gaussian variables, IID n01, then they cannot grow too fast. They cannot grow faster than square root of a logarithm. That's really a property of the fast decay of the tails of the Gaussian variable, as we will see in the proof. But that means that if you construct a process by taking linear combination of Gaussian variables, or you could take actually other variables that have sufficiently fast decaying tails, what you're going to have with your variables is a growth in n that's very mild, right? No more than the square root of a logarithm. So all you need to do is have coefficients that decay fast enough to guarantee convergence of the series. And these coefficients are certainly decaying to 0, and they have to decay reasonably fast to guarantee the convergence of that series of Haar functions, right? So that's exactly the way the proof is going to go. We're going to prove in lemma 3.3 that the Zn do not grow too fast, and then in our construction of the Brownian, we'll exploit that fact and the decay of the coefficients to show that this series converges in an appropriate space. So let's see the proof of lemma 3.3 first. Okay, so to see that, we're going to exploit the fact that Gaussian variables decay very fast. And that is to say that if I look at the tail, the probability that my Gaussian variable is very large, this decays, as you said, little x to infinity very quickly. Now, what is this probability? Well, we know what Gaussians look like. This is given by this integral The Gaussian measure is has a density with respect to the Lebesgue measure, and the density is a multiple of exponential minus y squared over 2. And I'd like to estimate that. You have this problem always that there's no antiderivative of this function in closed form, but you can make a rough estimate. All we need is sufficient decay in x, and that's why I've taken my x greater or equal to 1, such that I can multiply by y, which is greater than x and therefore greater than 1, in order to obtain here something that has an antiderivative, which is exponential, a closed form for the antiderivative, which is exponential minus x squared over 2. So the fact that the Gaussian density decays like exponential minus y squared over 2 tells me that the tail of the Gaussian up to some constant that I don't really care about, the square root of 2 over pi here, decays like exponential minus x squared over 2. All right? That's for every x greater than 1. So this is a very fast decay. Now, what does that tell me? That tells me for every fixed n, right, I could choose my x dependent on m. I could choose my x to be the square root of log n, which I expect will describe the potential growth. So I want to show that having Zn substantially bigger than the square root of log n is highly improbable. And really it is, because this is smaller than square root of 2 over pi times exponential minus log of n divided by 2. And just to simplify this matter, I want to get rid of this divided by 2. So I'm going to put a 2 here. So then I get a 2 there. And therefore I get a square root 2 upon pi exponential minus log of n, which is 1 upon n. Now 1 upon n is certainly a decay. It's not a very fast decay. In particular, this is not summable in n. So maybe to make things even faster, I'm going to multiply by some alpha greater than 1. And then I'll pick up an alpha in here and know my n is going to be raised to the power alpha. Okay. Now what does that give me? That gives me that this sequence of events, the events where Zn is greater than this multiple of log n, has to be, has probability that you can sum up. Okay, maybe you don't want to start an equal 1, because then 1 upon, and then n is, log n is 0, and okay, and this doesn't quite work because I want x to be greater than 1, but let's start at 2, and I have a sequence of events which probabilities can be summed up. Now this really means these events cannot happen particularly often, right? That's exactly the content of the Borel-Cantelli lemma. It tells us when you have a family of events which probabilities are summable, then these events can only happen, almost surely only happen finitely many times. So put in a different way, the probability that you have Zn larger than some multiple of log n for infinitely many n is 0. Okay, so up to a set of measures 0, my Zn is only greater than this multiple of log n finitely many times. So what does that tell me? That tells me that for almost every omega in my probability set, there exists a capital N, such that for any n above that capital N, Zn of omega divided by square root of log of n has to be smaller than square root of 2 alpha. So there it is. This variable Zn of omega divided by log of n is bounded at least for n large enough. But then of course, if I only look at finitely many n's, for finitely many n's, this is bounded by whatever the maximum of that is for little n smaller than capital N. And that is exactly saying that for almost every omega in omega, the supremum of n of Zn omega divided by square root of log of omega is finite. And it is the maximum of square root of 2 alpha, and my alpha was some fixed number greater than 1, and z, and the maximum of zn of omega divided by square root of log of n for n smaller than capital N. And this is exactly what I'm going to call C omega. Right? And that proves my lemma that up to a constant, which fair enough depends on omega, Zn of omega stays smaller than that constant times square roots of log of n. Right, so we cannot have growth in n particularly fast of Gaussian variables, and that is a consequence of the fact that Gaussian variables have tails that are very small tails, right? They decay, they cannot be large with high probability. So you cannot have too many of them large at the same time. Okay, that proves lemma 3.3, which is the key technical tool for what we're going to do next, which is prove the existence of the Brownian motion. Okay, time to construct our Brownian motion. So we have our IID sequence of n01 variable, and we're going to construct the Brownian as this series. So I'll show that this series converge and shows that this defines a standard Brownian. So to do that, first of all, I'm going to throw away a set of measures 0. So I'm going to take a set A included in sigma that has probability 1, such that for every omega in A, Zn of omega is, there exists a C omega, such that Zn of omega is smaller than C omega times square root of log of n, right? We know that this exists by lemma 3.3. And now I'm going to give myself two natural numbers. Let's call them capital M and capital N. Okay. And I'm going to give myself a t in 0, 1. And I'm going to look at this series, what is finite sum from capital M to capital N. Let's say that my capital N is greater than capital M of Hn, indicate a function of 0t times Zn of omega. I'm taking omega in A. What do I need to show? I need to show that uniformly in that parameter t, so with a constant that does not depend on t, these finite sums get small as capital M and capital N go to infinity. So I'm going to have the fact that I have for every omega in A uniform Cauchy sequence uniform in T. So I'm going to have convergence in the space of continuous function of the variable t. That's what I'm shooting for. So I need to show that this is small as capital M and capital N goes to infinity. Now, okay, this is what? This is certainly smaller than C of omega times the sum n equal m to capital N of square root of log of n, and then I'm integrating from 0 to t Hn of s ds. Right, and I need to show that this series, which is a series of number, is Cauchy. So the series of number with this general term is a Cauchy, converges because these finite sums are Cauchy sequences. Okay, now in order to do that, I'm going to need to remember what the Haar basis really is. And so it's better if I use h2k plus j, right, to remember the difference between the scale parameter and the position parameter in the Haar basis. So in order to do that, let me just have some notation. Let's call it maybe k of m and k prime of n be respectively the largest integer, such that 2 to the km is smaller than m, and the smallest integer such that 2 to the k prime of n is greater than n. All right, the point of that is that now the sum that I'm looking at here can be controlled by a sum of non-negative things over a larger interval n between km and k prime n. K between km and k prime n of the sum from j equals 0 to 2k minus 1 of square root of log of 2k plus j times integral from 0 to t of h 2k plus j of s ds. Right? I'm just re-indexing the element of my Haar basis as writing all the natural numbers as things of the form 2 to the k plus j for some k and some j, and then I want to make sure that I go from something that's literally of the form 2 to the k to something that's of the form 2 to the k prime. So, I go a little bit below that m potentially to have something of the form 2 to the km, and a little bit above that n to have something of the form 2 to the k prime of n. Okay, now what can I say about all of this? Now the key thing to realize is that although I do have a sum in j here, this sum is 0 for almost all values of j, except maybe 2 values of j in that sum. That's a fact we've used before about the Haar basis, but let me remind you how that works. So remark the integral of 0t h2k plus j s is 0 for all but 2 values at most of j between 1 and 2 to the k, between 0 and 2 to the k minus 1. So for k in n and t in 0, 1, this is 0 for all but 2 values of j. And why is that? Well, because of the support properties of the Haar function, and because they have mean 0. Right, this is the Haar function in some interval here that we've denoted by something like ikj. It's plus 1 on half of the interval, it's minus 1 on the other half of the interval. But if you integrate it up to a t which is here, then you're integrating 0. And if you're integrating up to a t that is there, let's do that in a different color, then you're integrating something that has mean 0. So the only way that you can get something non-zero is if your t is exactly in that interval. I should have it in a different color. So depending on your value of t, maybe it lands on the boundary of one interval. There's gonna be only for fixed t at most 2 values of j such that t is in the interval ikj. Okay, so this means that in that sum that we have here, right, this looks like a sum that could have up to 2 to the k elements, but it can actually only have 1 element because of that, well, only at most 2 elements because of that remark. So what have we got? We've got that this sum, right, that we're trying to show it's small, is certainly smaller than 2 times a constant times this sum from k to k prime of, let's simplify that a bit, 2k plus j here is at most 2k plus 1. So, and then I take a log. So what I have here is at most up to a square root of log of 2, which is some completely harmless constant. The gross I can get is at most square root of k plus 1. Right? That's what I get by taking the square root of log of something like that's like 2 to the k. And then my integral that I have here is what? Now I have to remember how my Haar basis is normalized. I was saying it's 1 or minus 1. It's not 1 or minus 1, of course. It's 2 to the minus, it's 2 to the k over 2, or 2 to the minus k over 2. And that's because the Haar basis is normalized in L two norms. If you remember the way we've defined it, we had exactly this factor, but it's only non-zero on a set of side lengths 2 to the minus k. So I'm integrating something that's at most 2 to the k over 2 on an interval which has side lengths almost 2 to the minus k. So really what I have is something that decays. So these coefficients that I care about, and I was saying, well, they have to decay, but we don't know how fast they decay. Well, no, we know. And we've made this computation, and they decay like 2 to the minus k over 2. So what we have is a sum from capital K to capital K prime. We have this growth, which is like a square root of k, and then we have this decay, which is like an exponential. It's 2 to the minus k over 2. So this series here, the series with this general term, very clearly converges very fast thanks to this term. Therefore, the partial sums have to be Cauchy. So this goes to 0 as km goes to infinity, or as m goes to infinity, because obviously if m goes to infinity, km, which is the closest value of k, so that 2 to the k is just a little bit below m, goes to infinity, goes to 0. Right. Now notice that the numbers that I've got here are independent of t. Right. The c omega only comes from lemma 3.3. It's only a property of the Gaussian variable Zn and the fixed omega I've chosen, and these are just numbers. So what have we proven? We have shown that the supremum over all t in 0, 1 of the sum from k equal from n equals 0 to capital M of Hn indicate a function of 0t so this, well, or I should say, this sequence of function indexed by the parameter m is Cauchy in the space of continuous function, and it's uniformly Cauchy. And now we know that uniform limits of continuous functions are continuous function. Get that from, say, analysis 1. Therefore, this limit exists. In the space of continuous function. Okay, so we have a well-defined process when we take this infinite sum. Not only that, but this well-defined process for every omega in A, so up to a set of measures 0, is continuous. So we have a well-defined process. I say well-defined because, of course, it would be ill-defined if these sums were to not converge for a set on a set of measure non-zero. We have a well-defined process. T goes to this. Satisfying. Well, it certainly satisfies property 1, because if I integrate from 0 to 0, I get 0. So all the coefficients will be 0. And it's continuous almost everywhere. Sorry, it's continuous everywhere almost surely. That's property 4. That's because the convergence that we got wasn't just a pointwise convergence for every value of t. It was a uniform convergence, so the limit is in the space of continuous function. So we have continuous paths for the limit. So we have a process satisfying 1 and 4. Now we need to show what? We need to show that the increments are independent and Gaussian distributed. Let's do that now. So to prove these two properties, we're going to use characteristic functions. So that's something you would have heard about in the probability course or in other stat courses. And you would know that characteristic functions determine random variables. So recall that if x is a random variable, then the function that sends y to the expectation of the exponential of I yx from R to R is called the characteristic function of x. And you can do that for a random variable which is real valued, or you could do that for a vector of random variable. It's called the characteristic function of x, right? And it characterizes x. So if x has the same characteristic function as a Gaussian variable, then x has to be a Gaussian variable. Now, for those of you who've done some Fourier analysis, of course, this is just a special case of the fact that you can invert the Fourier transform. What we have here is just the probabilistic version of the Fourier transform, and inverting that gives you your function back. So you might have to take that for granted if you haven't seen a proof of that the probability distribution of the random variable can be recovered from the knowledge of its characteristic function. But accepting this fact that functions are characterized by the characteristic function, what we need to show is that in order to show 2, we need to show that the expectation of exponential I y x t2 minus xt1 is exactly equal to exponential minus 1/2 of y squared times t2 minus t1. So let's give ourselves time intervals to start with. So let's t1 be smaller than t2, smaller than t3, up to some tn. Right. And to show 2, sorry, that's not 2, that's 3, we need to show that. We need to show that the characteristic function of an increment is exactly the characteristic function of a Gaussian variable with mean 0 and variance t2 minus t1. That's one of the things we need to show. And in order to show 2, we need to show that the characteristic function of a whole vector of such thing. So if you take the inner product of a vector or y in Rn minus 1 with this vector of random variable, take the exponential of that times the complex I, and then take an expectation. Right, we need to show that this really splits into and is really just a product of variables that only depend on 1j. So we need to show this. So tj plus 1 minus xtj, right? The fact that we have such a split here, so we say it has a tensor product form, will tell us that the probability distribution of this vector is really a product of the probability distribution of every single element of them. And that is precisely saying that the variables are independent. It's good, it gives the independence of the variable, almost by definition. So if we have that this characteristic function of the vector is really just a product of the characteristic function of the individual component, that will give us independent. And if we know that the characteristic function of the individual component are the characteristic functions of Gaussians, then we will know that the increments are Gaussian with the appropriate variance. So really what we need to do is study this function, a function of a vector in Rn minus 1, and show that it has the appropriate form. All right, that series of basic probability and the fact that random variables are characterized by the characteristic function, and that properties of characteristic functions of vectors characterize properties of the vectors of random variable in particular, the question of whether or not the joint probability is a product of the single probability, i.e. whether or not the different components of the vectors are independent of one another. So assuming this bit of probability theory, let's see how our construction, our candidate Brownian, does the job of being a standard Brownian, as independent increments, and these increments are Gaussian distributed. Okay, so I have to look at this characteristic function and try to compute it. So that's an inner product with this vector. Okay, so what is that? So this is an expectation of a sum, so that's certainly a product of expectations. Iyj xtj plus 1 minus xtj. Very good. But notice my product, it's an expectation of a product, not a product of expectation. So I haven't already proven 2, obviously. Like, I'm going to need some level of independence in order to exchange the expectation in the product. But what is this? Well, let's rewrite this expectation. Let's rewrite our candidate Brownian as a sum of IID, and independence is coming up here, of IID Gaussian. So it's the sum n equals 0 to infinity, Hn inner product with indicator function of 0 tj plus 1 minus Hn indicator function of 0 tj, and then times Zn. Okay, this can be simplified. Of course, this is just the inner product of Hn with the indicator function of the interval tj to tj plus 1, just by definition of these things as integrals. And now I can use the fact when the series converge uniformly, and what I have here is the expectation of a product j equal 1 to n minus 1, and an infinite product n equals 0 to infinity of the exponential of I yj times the indicator function of tj plus 1 inner product with the nth half function times a Zn. Right. Now, the good thing is, notice the following. This product and this expectation now can be exchanged because the Zn are independent. So by independence of the Zn, I have that the expectation of the product is the product of the independence of the expectation, sorry. So this is the expectation of the product, j equal 1 to n minus 1, exponential I yj, Hn. I should have said, it's not completely clear with that product in J here, so I should have got the product back inside, I suppose, at this stage, and written that as the expectation of I sum over J from 1 to n minus 1 of yj Hn times this indicator function, whatever that thing is, right? That is some number depending on n, and but that's not a random variable, that's just a number, and that's Zn, which is my random variable, and all the Zn's are independent, so I can make that exchange. Now, okay, I'm computing, so this is just a number, it's important to remember, and this is a n01 variable, so I know exactly how to compute such a characteristic function because I know what the characteristic function of a Gaussian is. So what I'm getting here is the what is it? It's exponential minus 1/2 times this coefficient here squared, right? Because this is the characteristic function of a Gaussian. again, if you haven't really done any competition with characteristic function, that's a fact you would have to remember. If you've done a bit of Fourier analysis or complex analysis and you've computed the Fourier transform of exponential minus x squared, then you would recognize this fact. But if not, just accept it that this is the characteristic function of a Gaussian variable at this particular value of y. Okay, now let's unpack that a bit more. Now here I've got a product of exponential, and that gives me the exponential of a sum. So notice this is why characteristic function of Fourier analytic techniques, by the way, are very helpful in probability. It's just because that independence and taking expectation and exponentials go very well together, right? That's properties of independence, the property of the product, and exponentials turn product into sums. So the two things are highly compatible. So I get a sum n equals 0 to infinity. I better not forget that 1/2 of these squares. So what have I got here? I've got the exponential minus 1/2 the sum over n 0 to infinity of an inner product of hn with a sum with a simple function really, which is the sum j equal 1 to n minus 1 of yj times the indicator function of the interval tj to tj plus 1. And then these coefficients that are coefficients in a higher basis are squared. So I have a sum of coefficients squared in an orthonormal basis. And so what do I get? Because the hn form an orthonormal basis, the sums of square of coefficient is exactly the inner product of this simple function with itself. Right? You can take this inner function, this simple function, decompose it into the higher basis, and when you take the inner product with itself, you get the square of the coefficient. That's exactly what being an orthonormal basis gives you. Okay, but now notice that because the interval are disjoints, or the way I've written them as closed interval only intersect on a set of measures 0 at just a point, these things are orthogonal, right? If j is not equal to k, the indicator function of tj plus 1 times the indicator function of tk plus 1 is 0. So in this double sum, I only really have a single sum. So sum j equal 1 to n minus 1 of yj squared times the indicator function of tj plus 1 with itself. All the cross terms are 0, since the indicator function of tj plus 1 inner product with the same on tk plus 1, whoops, sorry about that, is 0 if j is not equal to k, because they just have disjoint support, or support that intersect only on a set of measure 0. Okay, and what is this inner product? Well, you can compute it, and this is literally equal to the length tj plus 1 minus tj, the length of the interval. Okay, so what have we got now? So okay, it's an exponential of a sum, and so I can write it as a product of exponential, and that's exactly the product of the characteristic function of an n0 tj plus 1 minus tj variable. So this is the expectation of the exponential of I yj times x tj plus 1 minus x tj. So that gives me both independence and the fact that these variables x tj plus 1 minus x tj are Gaussian distributed, because that's what their characteristic function is. And that concludes the proof. That means this series we've defined really defines the Brownian.